Okay, so we just read a story about a child pulling a wagon, but before we get there, there's two different types of vectors that I want to talk about. One of them is known as a velocity vector, and what that represents is speed and direction. The other one is known as a force vector, and that represents the amount of force and direction. So, we have this child, right? Let's get back to the story. We have this child pulling a wagon with 40 pounds of force, don't we? And it says that the handle is making an angle with 30 degrees to the ground, correct? And they want us to find the vector. Well, here's the deal. So let's talk a second. We've got this force of 40 pounds, right? We've got this angle, which, by the way, if you remember a couple of problems we did, a couple of problems ago, we talked about finding the angles in the direction of the vector. So technically that angle is a directional piece of information, isn't it? Okay, so we've got the angle that's 30 degrees to the ground, and they want us to find the vector. Well, remember how we found the vector before in a couple of examples. To find the vector, we can take the magnitude of the vector multiplied, sorry about that, that was supposed to be a v. We can take the magnitude of the vector and multiply it by the unit vector, can't we? All right? So, the magnitude of the vector, in this case, since we're actually talking about a force vector, the magnitude of the vector is the amount of force itself. Because remember, vectors have direction and magnitude. And since the alpha, the 30 degrees, represents the direction, then the force actually represents the magnitude. When I'm finding this vector, I already know the magnitude of the vector. I know it's 40. Because the amount of force took the place of the magnitude. And I'm going to multiply by the unit vector. So that's I cosine of 30 degrees plus j sine of 30 degrees. Right? And now all I got to do is fill in the gaps. I need to know the cosine of 30 degrees and the sine of 30 degrees. Okay. Do you got it? Do you know the cosine of 30 degrees? Good. Square root of 3 over 2, right? And the sine is 1/2. And I'm going to bring this up over here. So the force vector that we're actually finding would be right? But you've got to reduce it. So my force vector for this child pulling a wagon looks like this. And again, the authors of the book will write this I at the end. So please make certain that that I does not look like it's under the square root. Otherwise, that is incorrect. Cool? Okay, so let me go back and recap. They were actually asking me to find a force vector. Well, it's still a vector, which means there's still magnitude, there's still direction. The angle was the direction, but the amount of force took the place of the magnitude, which is why 40 took the place of the magnitude of v. Cool? Okay, hang in there. Got another story for us. Okay, so we just looked at this second problem where they gave us this nice little drawing, right? And they're telling us we have two forces that are going on, and they'd actually like us to find the sum of the two force vectors. Well, here's the deal. Again, a force vector represents the amount of force and a direction. Well, since it's a vector has a magnitude and a direction. So the amount of force takes the place of the magnitude. So let's remember that. So the information that I have for that very first vector, and they called it F1, okay, is 40 newtons. And then its direction is 30 degrees. Good? Okay. The second one, sorry about that, I forgot my double lines, not a good thing to forget. And the second one tells us that we have this force, the amount of force being 60 newtons, and then its direction is a negative 45 degrees. Agreed? Okay, so help me out here. This negative 45 degrees, which quadrant is that in? Good, that's in fourth quadrant, isn't it? Which means a negative 45 degrees is exactly the same as a 315 degree angle, isn't it? Okay, good. So, they want the sum of the two vectors. Well, if they want the sum of the two vectors, I guess I'm going to have to find the vectors themselves, aren't I? All right, so let's look at the F1 vector, and that's how I'm going to call it because it's going to make it easier. So to find it, I need the magnitude of it, right, times that unit vector. Well, as we already discussed, the amount of force took the place of the magnitude. So it's 40 newtons in this case. The unit vector is I cosine of 30 degrees plus I sine, pardon me, not I sine, yeah, J, because we have a horizontal component and a vertical component. So that's J. Okay, so this F1 vector, and yes, cosine of 30 degrees, what is it? Good, square root of 3 over 2, and the sine, 1/2. This looks a little familiar, doesn't it? Okay, distribute the 40 and reduce. So I've got 20 square root of 3I plus 20J. Are you in agreement? Cool. Now let's look at the other force vector. And this one's for F2. So again, I need the magnitude of this vector multiplied by the unit vector. Well, the magnitude is 60 units because the force is taking the place of the magnitude, and I need the unit vector. So that's I cosine. Now you can put negative 45 degrees or you could put 315 degrees because they're actually in the same location. Either way. So I'm just going to write negative 45 degrees because that's what it actually gave us. Good. Okay. So help me out. What's the cosine of a negative 45 degree angle? Remember, it's quadrant 4. Good. That's a positive square root of 2 over 2. And what about for the sine of it? Yeah, quadrant 4, which means that's actually a negative answer, isn't it? So this is negative square root of 2 over 2 on the j component, isn't it? Okay, so let's distribute, let's simplify. We get 30 square root of 2i minus 30 square root of 2j. Agreed? Okay, what do we have to do now? Because they didn't ask us to just find the vectors for each one. Yeah, they wanted us to find the sum of them. They wanted to find F1 plus F2. Okay, now don't think too deep. Addition's pretty picky, isn't it? Can you add x's and y's? No, you can only add x's and x's. So can I add i's and j's? No, I can only add i's with i's, right? And j's with j's. So this is going to look funky, and since they didn't say anything about decimals, stay off the calculators. So I'm going to add the i's together, which means we get 20 square root of 3 plus 30 square root of 2 I, there's my horizontal component, plus 20 minus 30 square root of 2 j. And that is my vertical component, isn't it? And they don't want any decimals, so it's a funky looking answer, but that's what we get. Does this make sense? It's just like the last problem, except now I had to find two force vectors, and I needed to add them together because that's what they asked me to do. Hang in there. Got another one for us. Okay, so let's look at this last problem. They've given us a drawing, and I recreated it here so we could see. We have this 1,000-pound weight that's being suspended from two cables, right? And they want to know the tension on each cable. Well, when they want to know the tension on each cable, they actually want to know the amount of force that's happening on each cable. So here's the deal. Since they said tension, it's the same as force, which means I'm looking at force vectors again. Which means, though, in this case, I don't know the amount of force that's being placed on these cables. Which means now I've got to find the force. I have to actually find that magnitude. Are you with me? Okay, so for simplicity's sake, I'm going to do some labeling here. So we have things to talk about in a little clearer manner. So for at the 25-degree angle, I'm going to call it F1. So that's our first one. And at the 40 degrees, I'm going to call that F sub 2. Well, believe it or not, we actually have a third force. These two cables are holding this thing up, whereas this 1,000 pounds is pulling it down. So believe it or not, this 1,000 pounds is actually a third vector, a third force, shall I say. With me? Okay, now, you can look at this at a couple of different ways, all right? There's a couple different ways to look at what I'm about to show you next. Because I'm going to need, since I need to find the magnitude or the force at each of these vectors, I need to actually know the direction that they're going at least. And remember, the direction is also an angle. So I need to know the angle for the F1 vector and for the F2 vector. Okay? Now, here's the deal. Be very careful about the angles they gave you here, the 25 degrees and the 40 degrees. It's a little deceiving in terms of what those represent. So first and foremost, technically, isn't this a triangle created here? Good. And I can find the missing angle of that triangle because every triangle has how many degrees in it? Good, 180 degrees. And when I did my work, I found this to be a 115-degree angle. Are you okay with that? Good. Now, bear with me. I want you to see my drawing. If I take this line, that's basically the top of the box, and I extend it, wouldn't this line be parallel to the bottom of whatever's holding these cables, whatever these cables are attached to? They would be, wouldn't they? Okay, so those would be parallel lines, yes? And since they're parallel lines, that means, and yes, you kind of have to go back to geometry days, that means that this would be a transverse axis, which means this angle down here would actually be 40 degrees. You with me? That would actually be a 40-degree angle right here. Got it? Kind of back to geometry days, and it's important that we remembered that because that's going to help us with the F2 vector, and it's also going to help us with the F1 vector. So here's the deal. Let's look at the information that we have for the F1 vector. Remember, I'm looking for the amount of tension on it, right? I'm looking for its magnitude. I don't know it, so I'm leaving that alone. And I'm going to multiply it by its unit vector. Well, here's the thing. In order for me to finish this, I need to know the angle for the F1 vector, for this cable here. Remember, the angle goes from the positive side of the x-axis to where this cable is in this particular case. So this would be considered your positive side of the x-axis, which means when I start here and go to where this cable is, isn't this, when I add these two angles together, isn't this a 155-degree angle? The 40 degrees and that 115 degrees, doesn't that make up that 155-degree angle? Good. So this first vector, F1 over here, on the left side, shall I say, has an angle of 155 degrees. That's its direction. Got it? Okay. F2, the cable on the right. Again, I'm looking for its force, which means I'm looking for its magnitude, but I need its direction. And in this particular case, the direction for F2, again, you have to start at the positive side of the x-axis. The direction for F2 would be from the positive side of the x-axis right to the cable here. And isn't this a 40-degree angle for the F2 vector? Yes, it is. It is a 40-degree angle there. So, cosine, right, of 40 degrees plus j sine of 40 degrees. With me so far? Again, I'm looking for the force on both of these. I'm looking for the tension on both of these. But the angle for the F1 starts at the positive side of the x-axis and goes to here, which is why it's 155 degrees. And for the F2 starts at the positive side to the x-axis and ends here at 40 degrees. Cool? Okay, I mentioned there's a third one, F3, because as these guys are trying to pull this box up, this 1,000 pounds up, that 1,000 pounds is pulling itself down, right? Because that's gravity. It's trying to pull it down, isn't it? So here's the thing. If it's going down, is that a horizontal or a vertical? It's a vertical component, okay? It's a vertical component, which means since it's trying to pull it down, that's going to be a negative 1,000 pounds being pulled down in the vertical direction, which is the j direction. Cool? Okay, so far so good. Now, here's the deal. There's one piece of information that we need to know in order to start working with this together. And first and foremost, don't find the cosine of 155 degrees or its sine, neither for the cosine and sine of 40 degrees. Because those are decimals that are not ending decimals. And if you round it, you're not going to get the right answer. So we need to leave it just as I have written it. Unfortunately. But it's okay. It's not too bad. So let me get back to that missing piece of the puzzle that we actually need in order to work this out. What we need to know is this. We need to know that the equilibrium, because this is all a balancing act here. I have two cables pulling up, 1,000 pounds pulling down. I'm trying to balance it all together. Equilibrium is another word. As a matter of fact, they actually call it static equilibrium. And you're like, why static? Because they're not moving. Static means it's not moving. So that's why it's static equilibrium. And in order for static equilibrium to happen, then the sum of my vectors must equal 0. Got it? The sum of the vectors must equal 0. So here's the deal. That means I need to add all three of these together. Are you with me? Okay. We have some algebra to do at this point. So, keep those paper and pencil handy. Pause when you need to. I'm going to erase when I need to. Let's get working with this. Again, static means this isn't moving. This 1,000 pounds is just hanging. It's not moving back and forth on like a rail system or anything like that. But static equilibrium, for it to happen, all three of these vectors must equal 0. The sum of them must equal 0. So, I've got my F1 vector, right? I have to add it to the F2 vector, and then I have to add it to the F3 vector. So, if you allow me, I am going to do a distribution here. Okay? I'm going to do a distribution. Just making sure how, because I tried to make it as clean in my notes as possible. I can only add things that are the same. Do you agree? Okay. So, when I take F1, I am going to take its magnitude, and I am going to distribute it. So this is times I cosine of 155 degrees, right? But I can only add it to the other I, which would be the magnitude at F2 times I cosine of 40 degrees. Agreed? Remember, you're trying to add things that are the same. You can only add things that are the same. And I'm going to add the I components together. So, since all of this has to add up and equal 0, that means the I component has to be equal to 0. And so does the J component. These guys aren't going to get away with it, so to speak. They're not going to... They're going to basically cancel each other out. The I components and the J components basically need to cancel each other out if this is going to work out correctly. So, when I add all three of these vectors, I can only add things of the same. So right now I'm working with the I component. And I'm going to factor out that I, which means I have the magnitude of F1 times cosine of 155 degrees plus the magnitude of F2 times a cosine of 40 degrees. And that has to equal 0. Good? Now I got to talk about the J component. So, the J components, again, I'm going to take the magnitude of F1 and I'm going to multiply it by this J component. And I'm going to take the magnitude of F2 and multiply it to this J component. But I have one more J component. I've got that third one. We're minusing 1,000J. And that has to equal 0. So remember, these I components and these J components, when you add them together, they've got to basically zero each other out. So here I'm noticing that I'm going to factor out that J. And when I factor out that J, I'm left with the magnitude of F1 times the sine of 155 degrees. Plus the magnitude of F2 times the sine of 40 degrees minus 1,000. And this has to equal 0. With me? Okay. I need some board space, so bear with me a second. So here's what I'm noticing. I'm noticing that the I component and the J component, when I looked at them separately, actually gave me two equations, didn't they? And two equations with two variables. One variable is the magnitude of F1, and a second variable is the magnitude of F2. Okay, so I can't solve an equation with two different variables in it, can I? So that means we're going to have to use either the substitution or the elimination method in order to solve this. Now, elimination isn't going to work very well because when I take a look at this equation and the second one, how am I going to get the sine and cosine of 155 degrees to even match up? It's not going to work very well. Got it? Okay. But I am going to look at this first, this I equation. I'm going to look at that. And what I'm noticing is this. I'm noticing that when I multiply or divide both sides by the I, really, when I divide both sides by the I have just the equation left in the parentheses, don't I? I'm going to take this equation and I am going to isolate the magnitude of F1. So, when I do that, I get the negative magnitude of F2 times the cosine of 40 degrees. And then, to finish off isolating this magnitude of F1, I am going to divide both sides by the cosine of 155 degrees. Nothing but algebra. I know this looks funny, but this is nothing but algebra. I have two equations with two unknowns, and there's my challenge. And I need one equation all in the same variable. This equation is the easier one for me to work with. When I divide both sides by the I can either isolate the magnitude of F1 or the magnitude of F2 pretty quickly. So I decided to isolate the magnitude of F1. Which means I could substitute it in, couldn't I? Okay, so let's see how this works. Okay, I'm going to divide both sides by j, so this j is going to be gone. With me? All right. So I now have F1 equal to this lovely little fraction. So, cosine of 40 degrees over cosine of 155 degrees times the sine, I'm going to put it up top here, of 155 degrees. And then I'm going to add to it this magnitude of F2 times the sine of 40 degrees, and then minus 1,000. And it all equals 0, doesn't it? Okay. You know, I'm trying to solve for the magnitude of F2, aren't I? These two terms, the first two terms, have the magnitude of F2. Agreed? That 1,000 does not, does it? So what are we going to do with that 1,000? Are we going to leave it on the same side as the magnitudes of F2's, or are we going to move it over? Yeah, let's move it over. And if you don't mind, for the sake of some board space, I am going to add the 1,000 to the other side because it doesn't have a magnitude of F1. So I added the 1,000, or pardon me, it doesn't have a magnitude of F2. So I added the 1,000 over. Okay, stay with me. This looks really funny, but this is all algebra. Got it? This is all algebra. Okay, so I'm going to take out the magnitude of F2. I'm going to isolate it. And when I do that, I end up with negative cosine of 40 degrees times the sine of 155 degrees divided by the cosine of 155 degrees plus the sine of 40 degrees. And this is supposed to equal 1,000. Cool? Okay, so I don't know about you, But I know at this point to get this magnitude of F2 to be by itself, I'm going to have to divide both sides by this lovely bracket, aren't I? Here's the deal. Here's what I did first. Now that I actually have all these trigs like kind of isolated in a bracket, I actually punched this into the calculator to see what I would get. Like, what am I going to get if I figure out this fraction, multiply it by the negative, and add it to the sine of 40 degrees? What do I actually get? I know what I got. I got that this bracket equaled 1. It equaled 1. Like, how is that possible? Well, it's very possible. Because it looks like things are just basically canceling each other out. I have a cosine and sine of 155 degrees and a cosine and sine of 40 degrees, and it turns out in this case just to be 1. Does it always happen? Not necessarily, so don't think that. But in this case it did. So, I'm going to bring this over here. I end up with the magnitude of F2 times 1. That whole bracket goes to 1 equals 1,000, which means the magnitude of F2 is equal to 1,000 pounds. Which means the tension on this left cable is 1,000 pounds. Got it? The tension on the left cable is 1,000 pounds. This has 1,000 pound tension on it in order to hold up this weight. But I still need to find, whoops, I'm sorry, I'm on the wrong side. See, this is why I need you doing it with me. F2 was the one on the right, pardon me. So the F2 has 1,000 pound tension on it in order to hold its end up of the cable. Got it? Okay. But I still need to know the tension on the left cable, the F1. So, I know the magnitude of F2 is 1,000 pounds, don't I? So right here then, the magnitude of F1 is going to be equal to negative 1,000 times the cosine of 40 degrees all over the cosine of 155 degrees. And when you punch that into the calculator and work that all out, we get that the tension over here on the left side is approximately 845 2/10 pounds. 845 2/10 pounds. That's the tension. That's the force that's on the other cable over here. Cool? Okay. Here's the deal about this problem. You had to set up 3 vectors. That was simple enough to do. But then you needed to actually know one little fact, and the one little fact was static equilibrium. Because this is static, the weight's not moving, it's static. And in order for the equilibrium, right, equilibrium means balance, all 3 of these vectors added together needed to equal 0. So if they needed to equal 0, and I'm adding, I can only add things that are the same. So I added the I components and the J components together. And basically, these components had to cancel each other out in order for us to be equal to 0. Which means the I component had to equal 0 and the J component had to equal 0 in order for us to get a sum of 0. At this point, it was a bunch of algebra to work on. So I recommend pausing this, going back, playing it, and pausing it where you need to make sure you understand the algebra. Because to be honest with you, this looks a lot more complicated because I had to leave the cosine and sines in there. Because if you didn't, and trust me, I tried it, if you didn't, then you did not get these exact answers that you needed to get. Cool? Okay, so, again, we ended up with 1,000 pound tension over here on the right, and 845.2 pound tension on the left side to hold up this 1,000 pound weight, or 1,000 pounds of whatever it is that they're trying to hold in midair. Cool? Okay, so you guys have fun with this stuff, and I'll catch you on the flip side.